Very good. I'm just trying to see how I can. Now I don't see any of you anymore, but I hope you're still there.
Okay,
Yeah, we are
please.
still there.
Yeah, we are
Perfect.
here,
Yes,
but
very good.
just
I'm very happy
okay.
to. I'm very happy to be back again. And again, I'm very sorry that I'm not there with you in person, but I'll try my best to give you a lecture today that is understandable and also covers the things that I wanted to say. So let me just briefly remind you what we have seen yesterday. So yesterday we have begun to talk a little bit about how groups act on vector spaces, how this gives rise to what we call symmetries. And today I want to look a little bit more on the algebraic side of this picture. And namely, I want to give you a small panorama of invariant theory. Okay, this is actually a very exciting topic that has laid foundations of modern algebraic geometry. But before we start, I want to talk a little bit about what we actually mean when we talk about invariance, because talking about invariance is actually something that is more general than just what we talk about in algebraic geometry. So, I mean, if we are very naive and very uh, only talk about the word, an invariant, that if we talk about, for example, with my mother, she would also agree with the following definition. An invariant is something that remains unchanged. So whenever, I mean, this is just a very vague definition still, it's not a real mathematical definition. So what we mean is a quantity or an expression that stays the same, maybe under a certain process, a transformation, or an operation. So this is a very loose definition, of course, still, but I mean, in this very loose definition, I mean, you know examples from mathematics already. For example, if you look at the complex number, then you can look at its complex conjugate. So this is two complex numbers, and the two complex numbers will share obviously the same real part and the same absolute value. So whenever you have a complex number, the real part and the absolute value of the complex number are an invariant, with the transformation being the complex conjugation. More fancy stuff. I mean, for example, if you look at topological manifolds, then homology, cohomology groups, they also are invariant
Excuse me, Cordian.
topological objects.
Uh,
We can't see your slides. Did you share?
Oh,
have you shared?
okay, very good, very good. Maybe we try to do this again. I'm sorry for that. I'm sorry for that. That's the problem when you're not there in person. Can you see the slide now?
Not, yeah, we can see the slides now. Maybe you
And
enlarge
also,
it.
if I go onto full screen mode, is it still there?
Yeah, now we can see that. You can start again.
Perfect. Sorry for that. Sorry for that. So what I wanted to say was this loose definition of an invariant, something that remains unchanged. And I have already mentioned the first example here. The first example being this real and complex, this real part and complex absolute value. Or if you want to be a little bit more outside of mathematics, in physics, if you have a physical system, then the total energy of this physical system is something that remains unchanged over the evolution of this physical system over time. So, I mean, whatever this physical system may be, we believe that the total energy does not get wasted. So, I mean, you can retrieve this information throughout the evaluation of this system. Okay, again, this was a very loose, I mean, suite of examples that were just trying to get you a little bit in the spirit of what invariant theory should actually help us to understand. Namely, it should understand a little bit how we can think about things that remain unchanged under processes. Okay, now let's start a little bit with the historical background. So this was actually the following was actually a very interesting topic of mathematics in the 19th century. So we start with a binary form of degree 2, which is just a polynomial of degree 2. in two variables that is homogeneous. So it's a polynomial P in the variables Z and W, which is given by obviously three coefficients, P1, P2, P3. So you can write it as P1Z squared, P1CW, P3W squared. Okay, so whenever I give you three complex numbers, P1, P2, P3, you can build such a polynomial. Now, there is a very interesting group. I mean, this is the following group, namely the special linear group of order 2, which is all the 2 by 2 matrices with determinant 1. Okay, so this is a group you have maybe seen already in your life. And this group gives a linear change of coordinates on the two-dimensional vector space C2. Okay, so I mean, this acts just by change of coordinates. And in the language of yesterday's lecture, I have this group and I have a two-dimensional representation of this group. Okay, so I have the setup. Now, when I have this two-dimensional representation by coordinate change, actually this group, my group, also acts on the binary forms that I have. How does it do that? Well, I mean, if I take my variables and I just apply the linear transformation of the coordinates to the variables in the polynomial, I obtain another polynomial, P prime, which is just the original polynomial evaluated at the coordinate changed coordinates. So this is a new polynomial with coefficients P1 prime, P2 prime, and P3 prime. Okay. So does that's not too hard to see. So actually what we were doing is, so I take a 2 by 2 matrix out of this special linear group, and I make this group act on a three-dimensional space just by seeing, I mean, I just really do the transform of coordinates and check how these new coefficients come from the old coefficients. And what you will find is that this is just a matrix M of A that I associate to my original matrix A that gives me the change of coordinates of my binary forms. So my new binary form, P1 prime, P2 prime, P3 prime, which are the coefficients of my new binary form, they are just given by applying my matrix MA to the original coefficients. Okay, so this is very, very simple and very concrete. So what we have just what we just have done is we have created a new representation for our group SL2, and this time my group SL2 acts on a three-dimensional space. Okay, so in yesterday's lecture's notation, we have a three-dimensional representation of SL2. These two are obviously linked to each other. I mean, this one, the new one, is sort of coming from the old one in a very, very obvious way. Okay. So as I said, this was already considered by people in the 19th century. And one interesting thing that they realize is the following. So now look at another polynomial. So this is another polynomial in now three variables, x1, x2, and x3, which is just given by x2 squared minus 4 x1, x3. So people who have paid attention in high school might immediately recognize this polynomial. And I give you maybe 2 minutes in the break to think about where you have seen this polynomial before. But what is interesting about this polynomial delta is the following. If I take this polynomial delta, so it is a polynomial in three variables, I can plug in for the variables the coefficients of my binary form. So this is a little bit problematic to get one's head around. So I have polynomials. I view those polynomials as points in three space with the coordinates P1, P2, P3. And then I have another polynomial, delta, and in delta, I plug in the coefficients of my original polynomial. Okay, so now there is a little bit too many polynomials, namely going around, but I hope you bear with me for a moment. So if I do this, I evaluate my polynomial at its coefficient, at the coefficients of a binary form. I just plug it in. I get the second coefficient squared minus 4 times the first coefficient P1 times the last coefficient P3. Okay, that's very simple. So why did we do that? So what is actually interesting, and this is a very easy calculation to do, which I invite you to maybe do if you don't trust me. I could also, of course, start with my polynomial P1, P2, P3, and calculate a corresponding new polynomial for a given element of SL2, which will be would P1 prime, P2 prime, P3 prime. And I could evaluate also my polynomial delta at the new polynomial that I get. So suppose Thomas gave me another polynomial, P1 prime, P2 prime, P3 prime. I plug it in, and the magic that happens is that I actually get the same value back. Okay, so the magic being I get the same value as was obtained by the original polynomial. Okay, so another way of saying this discriminant delta is left invariant by the action of SL2. So this is kind of fascinating, because if Thomas hands me two polynomials and claims that they are from the same orbit of SL2, how would I know? I mean, now here I have a way of checking, namely I can check if they have the same discriminant. And if they don't have the same discriminant, then they better be not in the same SL2 orbit. Okay, so what is very interesting
is it
that
left? Is left like you're saying it remains invariant?
Yeah, it remains. Sorry, yes, that's a very good question. When I was reading it out loud in my head, now I had exactly the same problem that I said, oh, it's a very unprecise. I mean, by left invariant, I just mean not left invariant as if I have a left action. Sorry for that. It's just fixed. Yeah, I should have said fixed. Very good remark. Sorry. So in fact, what one can show is that this is what we call a fundamental invariant. So fundamental invariant means that any other polynomial Q in 3 variables that has the property that it stays fixed, that now I don't want to say left invariant again, but that it doesn't change under applying the action of SL2, then it can be written as a polynomial in this fundamental invariant delta. Okay, so again, this is something that people are already starting with Gauss have been interested in looking at for binary forms, and this was a pretty important business in the 19th century. When you generalize this, of course, you can look not only at binary forms of degree 2, you can look at binary forms of degree 3, binary forms of degree 4, 5, 6, and so on. And a lot of the names of the mathematicians that you see in here, you have maybe already encountered, maybe even in the course so far. So a lot of the techniques from computational algebraic geometry have been actually inspired by those people studying binary forms. So, and what was a very important result in this area was by Paul Gordon in 1868. He could actually show that, I mean, the example that we had with the degree 2 binary forms is in no ways unique, in the sense that for every degree, therein exists a finite system of fundamental invariants, okay? So for every D, we have finitely many invariants, fundamental invariants, with the property that every other invariant for binary forms of degree D can be expressed as a polynomial expressions in those finitely many invariants. Okay, so this was a big theorem in the late 19th century, or in the second half of the 19th century. And I mean, even though we know that these exist, it's actually quite challenging to get them for an explicit value of D. Okay, so this was a little bit a historical background to developments that I want to come to. So let's try to be a little bit more mathematically precise. and define a little bit more what we have done. So again, I start with the group G. Most of the time today, my groups will be actually finite groups to simplify some things. So of course, a lot of the definitions work also for all kinds of groups, but I mean, it's no problem if you just think about finite or compact groups. So, and I have a linear representation. Again, this was a group homomorphism from my group G to some group of invertible endomorphisms, some invertible matrices. Okay, so starting with this representation on my vector space C to the n, I can define a new representation, a new action of my group on the polynomial ring by just saying, well, I just take my action or my representation to be just, I mean, take the polynomial and let the linear group action. So this is just a matrix here. This row G to the -1 is just a matrix. And I let this matrix act linearly on the variables. And I do this for all G in G. Okay.
Is rho is same as
G
theta?
or mu G?
Sorry?
Rho, what is rho here? Is the same as the representation theta?
Oh yes, you're absolutely right. I'm sorry for that. Yes, that's a very good point. That's a very good point. Yes, these letters look alike, but yeah, you're absolutely right. That's, I mean, that otherwise it wouldn't make sense. Very good remark. Okay, so we have this representation, and we build a new representation just by extending my action very naturally to variables of polynomials. And then, of course, we say that the polynomial that does not change or that is left invariant, even though I come from the right now, is invariant if it doesn't change. If it's left invariant by all elements of the group by this action. Okay. And I mean, we will write for all invariant polynomials, we will just write the polynomial ring upper G will denote all invariant polynomials. That is, all polynomials that the group action does not do much to. That's another way of saying this. Okay, so this is the way I defined it now. It's just a subset of polynomials.
I have a question here.
Sorry?
What do you mean by all invariant polynomials? Because these invariant polynomials are depending on G and as well as on the representation.
Oh, for a group G and the representation. You're absolutely right. So this depends I mean, so the group and the representation are fixed. Whenever I don't say anything, they are fixed. Exactly. Very good remark. Then I mean, this is for the group action. Yes, this is why yesterday said sometimes this whole business is a little bit tricky. Normally, you would always need to carry with you the actual group action, how the group action is on the vector space. And people become very sloppy like me. They mix up letters and they also just leave them then out to not confuse the audience more. So we have just this group. It acts via this linear representation on my vector space. And this gives a new representation on the polynomial ring. And the polynomials that are left invariant, so that are invariant with respect to this action, I just denote by polynomial ring upper G. And I mean, it's very easy to see that this is not just only a set, but that this is actually also a ring of its own right. So very sure to see. I mean, if I take two polynomials that are invariant with a linear action, I add them together, I get the same kind of polynomial back. If I multiply them, I also have the same property. Okay, so this set of polynomials that are left invariant by a group action is not just a set, it's actually a ring of its own right. Okay, very good. Let's just look again at one simple example. So I now look at the group symmetric group on 3 letters. We have yesterday seen this is just a group that permutes a set with 3 elements, and it has a permutation action. So it permutes the 3 coordinates in a 3-dimensional vector space, C3. And so I can just imagine that this flips the coordinates of my polynomials. So if I take, for example, the element, which in this notation 1, 2, I just mean it's the element that flips 1 and 2. and leaves leaves the element 3 unchanged in my set, and I apply it to the polynomial f, which is x1 minus x2, then obviously by this action I get a new polynomial, which is x2 minus x1, because I just flip the 2, and this is minus f again. So this polynomial f is mapped by my element sigma to its negative. So in particular, it is not invariant. Okay, very hard to see. But you maybe also already have seen those polynomials. So there are polynomials that are invariant. So for example, if I take the sum of x1, x2, x3, I mean, obviously, whenever I interchange 1 and 2, 2 and 3, 3 and 1, nothing changes with this polynomial. It's just, I mean, reordered. The terms are just reordered. The same for the second polynomial that I have here, which is x1 times x2 plus x2 times x3 plus x1 times x3. So also this polynomial doesn't really, for this polynomial, it doesn't really matter whatever permutation I apply to it. So it's also invariant. And finally, also, of course, x1 times x2 times x3 is an invariant polynomial. Okay, so these polynomials you maybe have already seen. They are called the elementary symmetric polynomials. And the study of these elementary symmetric polynomials actually predates the study of invariant theory, as those have already been studied by Newton to see the relationship between roots of polynomials and coefficients. If you remember from high school, if you have a polynomial of degree 2, of degree 3, and you want to look how the coefficients of your polynomial correspond to the roots of the polynomial, then there is this theorem called Vieta's theorem that exactly tells you that these polynomials here are exactly the coefficients of a polynomial of degree 3 in one variable t, when x1, x2, and x3 are the roots. Okay? Very good. So an interesting fact, which one can prove rather directly, is that if we look now, or this should be an Sn, sorry, this should be an S3 here, not a G in general. If I look at the polynomials that are left invariant with respect to the group S3, then, I mean, we have already seen this is a ring, but moreover, this is actually a polynomial ring, namely it's the ring generated by these 3 polynomials, okay?
Excuse me.
Elementary symmetric polynomials.
Excuse me, Cordian,
Yes?
when you are taking the collection of the polynomial which are unchanged under the group action, so only those polynomial will be a part of the algebra who are invariant under all the operations, or for the one, just like if
No,
something
for
is
all.
for
okay.
all. Okay.
For all, yes. I mean, G here should be S3, and then this means these are the polynomials that are invariant with respect to all elements
okay.
of all elements of S3. So here we have seen in the first example, we had seen one polynomial that is not invariant with respect to one specific coordinate change. So it's then particularly also not an invariant. And theoretically, for these 3 polynomials, I will have to check for all
For
the
all.
permutations.
Okay.
Okay,
So
very
can
good,
you
very good.
again redefine the action of S3? I did
So
not
the
attend
action is
yesterday.
just, okay, the action, so the action is just, you have this action on the vector space. So it changes the coordinates. And what we do here is now we just change the variables accordingly.
I'm talking about the action of S3 as you have mentioned that you have defined yesterday. Yeah.
Yes. So I mean, the
which
action is
that?
okay. So the action is if I change, for example, in my example above, if I change 1 and 2 in my set, I also change the indices of the variables accordingly. So x1 minus x2 is mapped to x2. So x1 is mapped to x2, and x2 is mapped to x1. So x1 minus x2 is mapped to x2 minus x1.
Okay.
Also, is there any algorithm to know which polynomials will generate this ring?
Very good question. We will come a little bit to that, but this is a very important question. So here here I just said very bluntly that you can actually show this theorem and very nicely with Gribner basis techniques, because I mean you can actually show that these polynomials, every other polynomial that is S3 invariant can be written in those polynomials by actually looking at a very good term order and doing this expression very concretely. So this was already observed by Gauss in the beginning of the 19th century, and this is very nicely explained, for example, in the book by Cox Little O'Shea in chapter 7, I think. So I mean, for this, for this specific group, it's very easy to do that, but we will come in a minute to the problem that this is not actually always easy. Let me just briefly also mention another example to come away from the example that I had. So I have another group, namely a cyclic group of order 4, which I let act on a two-dimensional vector space by 90-degree rotation. So again, a cyclic group of order 4 is the group of 4 elements, yeah? And I now realize this group by matrices, namely those 4 matrices. And if you look at these matrices, what this group then does is just it takes a vector in 2 space and rotates it 90 degrees. Okay. So then I also get, of course, an action again on the polynomials, and it's a little bit tedious maybe to see, but for example, the first P1, the square of the variables is not affected by any rotation, obviously. So I mean, if whatever I rotate in 2 space something, the absolute value of the vector does not change. So the square of the variables, the sum of the squares of the variables, is in particular also left invariant for this group. When you also see that what happens is that, for example, x can be mapped to minus x or y can be mapped to minus y with these matrices, then it's obvious, it's very easy to see that also the second polynomial, x squared times y squared, stays invariant. And in fact, there's also a third polynomial that we can find that is left, that is again, I use this word left invariant too often. It's not left invariant, but it's just fixed by this action. So we have these 3 polynomials, and to all the 3 polynomials, my rotations do not do anything. So whenever I apply a rotation to the coordinates, I get back the same polynomial. And what one can actually show is that these 3 polynomials, they now generate the ring of invariance. Okay, this is again maybe a little bit out of the blue, but I want to actually use this to come with a very interesting first observation. I started with the polynomials in 2 variables, and now I have a polynomial ring in 3 variables. I have a ring generated in 3 variables. So what you all immediately see is that there is a mismatch of 2 and 3. So these 3 elements that I have here, pi1, pi2, and pi3, they can no longer be algebraically independent, right? So there must be algebraic dependencies amongst them. And in fact, if one does the math, one finds that actually the first squared is the same as the second cubed plus the third squared. Okay, so we have this operation. We still have a ring that is finitely generated. However, it is not freely generated. Okay? There are dependencies amongst the polynomials. Okay, so we have that actually we have to mod out these relations. Okay. Wow. So this was now just some examples to see what kind of objects we're looking at. And now I want to use the magic of algebra to help you to see that this theorem, that the theorem that I will come into in a minute actually holds. So the magic of algebra comes in form of a very interesting map, namely the following map that we implicitly have already seen yesterday. And this map is called the Reynolds operator. And this is now here only defined for finite groups. And I'm just saying this for those of you who are interested in non-finite groups. This can be also defined for other groups, infinite ones, compact ones. And then all of what we're doing later will actually work exactly in the same way. But just for simplicity, for the reason of simplicity, let's just look only on finite groups. So what I now look at is the following operator. I take a polynomial which is not necessarily symmetric, so any polynomial, and I map it to the following sum. So I sum over all elements in the group. I let the group act on my let this element act on my polynomial. So it gets, my polynomial in general gets mapped to another polynomial, and then again to another polynomial. I sum all of the orbits that I get in this way up. So I take the sum over all the elements that are in a G orbit of my original polynomial f. And at the end, I just divide by the cardinality of the group. So I average over the group action. Okay. So this is called the Reynolds operator. And let's just, for simplicity, for the sake of sanity, check that the thing that I get at the end actually is an invariant polynomial, because I claim here that this is actually defining an operator from that eats polynomials and gives us back invariant polynomials. And obviously, I mean, if I start with any polynomial and I look at this sum, just the way that how the sum is made up, if I have my group acting on it, the group will only rearrange the summands, but the sum itself will stay will stay the same. So I will end up with an invariant polynomial. Okay, and I mean, I just do this. I mean, this averaging is maybe not important for the moment. I just do this to make sure that when I actually plug in an invariant polynomial to begin with, then I get back my original invariant polynomial. Okay, this is why we do this averaging here. Okay. So I hope the definition of this operator is fine. And let's just see three very simple properties. So the first property, which is obvious, is, I mean, the polynomial ring is in particular a C vector space. And so this is a sub, and the invariant ring is a sub vector space. And this map is just a linear map. Okay, very easy to see. The second one is, and this is again why I defined this 1 over G in the beginning as a normalizing constant. This will actually give a map that is constant on the subring of invariant polynomial. So it's a projection, if you want. So if I start with an invariant polynomial, I will get back the same invariant polynomial. And the last property is the most important one. Our operator is actually not only C-linear, but it is actually linear with respect to the subring of invariant polynomials. That means whenever I take an invariant polynomial times a normal polynomial, and I take the Reynolds operator of this product, I can take out the invariant polynomial in front of the operator. Okay, that is what I mean by invariant ring linear. Okay, this is just coming from, I mean, if you take a little bit time writing out this definition carefully, I mean, this is just distributivity of sums actually. So these three properties are actually very simple to prove and very simple to verify. And also this operator looks very harmlessly defined, but is actually a very powerful tool. And with that, I want to come to one of the most magnificent theorems of the 19th century, which is the following theorem of Hilbert. Remember, Cordian, so roughly 30 years before Hilbert gave this theorem, had shown that, or maybe 20 years, had shown that that the invariants for these binary forms are always finitely generated, so that there's always a finite set of homogeneous invariants. So what Hilbert could show is actually that this holds for any finite group, and I mean even more general for all groups where we can have this Reynolds operator. Namely, he showed that then so if I have a finite group, then this invariant subalgebra, oh, this should be a C here, but I mean, I of course would also hold for other fields of characteristic zero, is generated by finitely many homogeneous invariants. So there always exists a finite set of homogeneous polynomials pi1 to pi m, such that every other invariant polynomial can be written as a polynomial in those fundamental invariants. Okay. Now, I was stressing very much that this result was very important, and actually it was very important, and we will see the proof of this in just a minute. But let me say, the proof of this was actually the start of modern algebra and also the start of something that Paul Gordon called the theology of mathematics. So we will see the proof in a minute, and the proof is non-constructive. And this is why people in the 19th century actually, I mean, Paul Gordon said that this is no longer mathematics, this is actually just blunt theology. Things you have to believe, but you don't actually get something concrete in your hands. Just as a small remark, so as you know that Hilbert posed a list of problems at the International Congress of Mathematicians in Paris. And he actually, one of the questions that he asked was if this theorem holds for any group. And turns out that no, it doesn't hold for any group, although for a large group of class of infinite groups, we can actually use the same proof. But Nagata proved actually that there are counterexamples to the statement. So not every group has this very nice property that there are finitely many fundamental invariants. Okay, let's just quickly look at the proof, and because the proof is very beautiful and actually not hard to see. So what we do is we look at an ideal. We look at an ideal generated by all invariant polynomials of positive degree. Okay, so I look at all the polynomials that are invariant. Of course, constants are also invariant, but I forget those because that would be bad to look at them. I take the ideal that is generated by all the polynomials of positive degree. And by ideal now, I mean, and again, I screwed up this with the K and the C, I mean the ideal generated in the polynomial ring. Okay, I have the polynomial ring, my invariants are a subset, and now I look at the ideal that they generate. Now, another way of saying this is just I look at the ideal generated by the Reynolds operator of all monomials. Okay. Now, and I think you all have heard about Hilbert's basis theorem. Hilbert's basis theorem, so this is an ideal. We don't know a lot about this ideal, other than it is an ideal in our Noetherian polynomial ring. But then we know by Hilbert's basis theorem that this ideal is finitely generated. So we know that there are some polynomials I1 to IM which generate this ideal. Okay. So the interesting thing now is, and this is essentially the claim or the actual proof of the theorem, is that not only do they generate the ideal, no, they already generate also the invariant ring. So this should be, this should be a G here. So the invariant ring is the same as the ring generated by those invariant polynomials that actually give us the ideal. Okay, and to see this, we will now make a proof by contradiction. And this is where the theology comes into play. So if this were not the case, so we can always pick a polynomial I, which is invariant, but not yet a polynomial expression in I1 to IM. Yes? I mean, that's by contradiction. We assume it were not the same, so then we can always find such an I. And if we can find such an I, we can also take one of the minimal degree. Okay, so let I be a polynomial that is invariant, but not expressible as a polynomial and identity in the I1 to IM. and let it be of minimal degree and not constant. Okay, so now we have, on the other hand, that I is in this ideal IG, right? I mean, this is also just a triviality. So because it is in this ideal, I can write it as a sum, a combination of my polynomials I1 to Im times some polynomials fj. So, and these polynomials fj, they are not necessarily invariant, of course. They are not invariant in general because I look at the ideal generated as a sub-ideal of the polynomial ring in general, but I know that their degrees are at most the degree of I. So now the only thing I need to do is now I apply the Reynolds operator. So my polynomial I is itself already invariant. So we know that applying the Reynolds operator to it will not change anything. And because of the linearity and the linearity over the invariant ring, I can just write the application of the Reynolds operator in this form. So the Reynolds operator is nothing else than the Reynolds operator applied to these polynomials fj times ij. So now, remember, I mean, take a look at this expression that we have here. So ij, they are already invariant polynomials, and also the Reynolds operator applied to fj is an invariant polynomial. And because the degree of these fj's is smaller than the degree of I, we can assume that we have to have that they are already because we assumed the minimality of the degree of I, and we have that the invariant polynomial that we get if we apply the Reynolds operator to fj is already expressible in the ring. A1 to AM, and in that we already have our contradiction because that would then also imply that I already is in that ring. Okay, so this is a very beautiful proof, and a proof that actually shows us very nicely how these things come together, invariant theory and algebra. So I want to jump a little bit and talk a little bit about because we will need this tomorrow in the exercise, in general, how this looks like for symmetric polynomials. So there is two families of symmetric polynomials that you have surely seen, and I just recall them briefly. So one is the so-called power sum polynomials. So this is the polynomial pk, which is just the sum over the variables raised to a power k. So obviously this is left invariant by my group action. And the elementary symmetric polynomials, ek. Okay, so the important result to know or to remember is that these two families actually are both algebraically independent, and they span the Sn invariant polynomials. So every Sn invariant polynomial in n variable can be written as uniquely written as a polynomial in either P1 to Pn or E1 to En. Okay, so this is maybe a time to ask, are there any questions at the moment?
Oh, so far so good, I think. Yeah. So far so
not.
good.
Very good.
No, there is no question.
Very good. That either means I did a very good job or I did such a bad job.
Yeah, you are
everybody's
doing a
already
good
asleep.
job. Great job.
Okay. Okay, so now we have seen that we know that every invariant ring is generated by polynomials, and we have seen now in this one example of the symmetric polynomials that we can always find n generators. So in general, we have also seen in one example that we maybe need more generators, but from the theorem of Hilbert's, it remains absolutely unclear how many generators we actually need. And as I said, this whole development started with Hilbert, sparkled a whole interest in commutative algebra. And I just want to mention one result, which is due to Noether, which says the following. So if I have a finite group acting again linearly on the vector space, I get an action on the polynomial ring, I look at the invariant polynomials, then I can, then I know that I can always find a generating set of cardinality at most n plus the cardinality of G over n. So this is a binomial expression in n and the cardinality of the group. And furthermore, she could show that the degree of my generators will never exceed the cardinality of the group. So if we just naively now, just for the sake of sanity, let's just, forget the previous result that we knew about the symmetric polynomials and just plug in the numbers for our group, symmetric group, maybe of order 4. So we would have n equals 4. N factorial is 12. No, n factorial is 24. Sorry. So we have 4 times 24 is 28 over 4. That's a pretty big number. That's so big that I cannot really calculate it right now. And the degree of my polynomials would be at most 24. Luckily for the group of Sn, we knew that actually 4 are sufficient and their degree was actually bounded by 4, which immediately shows that Noether's bound in general is maybe not the right one to choose, but at least it gives you a very concrete upper bound. And I mean, in principle, it gives you a way of checking for invariance. Namely, I mean, you only need to check all the polynomials up to this degree, the cardinality of n, and you need to have so and so many generators, and then you can be happy.
Cordian,
Yes?
yeah, are there some generator having the degree greater than the cardinality of the group? If you go back to that Noether's theorem.
Yes?
So are there homogeneous invariants exceeding the order of the group?
I mean, there are
And in the-
invariants that exceed the order of the group.
Yeah.
Yes. I mean, for
And
example, if I
in
take,
the generating set as well.
sorry?
So in the generating set of algebra.
No.
No. Okay.
No. I mean, of course, I mean, okay, you can always add whatever element. I mean, if you have a generating set, you can add one, a redundant one, so then yes, but you can always find one that is at most, looking at the polynomials of at most degree, group size will be always sufficient. And we will see maybe in a minute why this is the case.
Okay. Okay.
Okay, so I also wanted to give a nice connection to geometry, so which will be important tomorrow a little bit, or on Thursday. So if I take those generators, so I have m polynomials, I have my invariants, I have m generators, so then I can actually also look at a very interesting polynomial map. Namely, I just look at the map that is defined from Cn to Cm, which just takes, again, I have screwed up the A here, I'm sorry for that, which takes a point A in Cn and maps it to the evaluation of the generators that we have chosen, right? So I take a point in Cn and I map it to a point in Cm with m polynomials. That is a fancy word, it's called a morphism, but it's just a polynomial map. And this polynomial map is called the Hilbert map. Now, why is this interesting? So I also look at the following, namely the orbit, just for the notation. I mean, if I have a point in Cn, then I will just look at all the points that are my point A is mapped to. I will call this set the orbit of my point, and I will denote it by G of A. Was there a question?
No, I think that's typo. I think X is A actually.
Yes, I'm sorry. This is like always, when you prepare these slides, you have so many thoughts and then you type it in LaTeX and then you never see the obvious things.
This is good to keep doing these typos so that
Yes.
keeping
Exactly,
everyone
it's very
intact.
good. It's very good.
So you
Exactly.
can see that the
This was
audience
all
is
magically
not
planned. You know, all my mistakes are here by purpose to make sure that somebody finds them.
Yeah.
Unfortunately, this is not true. Okay, so the interesting thing is now, if I take a finite group and I look at this image of this polynomial map, then this is exactly the algebraic variety which is defined by the, so this is a map that lives in CM. The image lives in CM, but we have already seen that these polynomials, they are in generally not algebraically independent. So there are some algebraic dependencies on them. If I mod out those algebraic dependencies, I get exactly the image of my variety. Or in other ways said, I mean, maybe in a more fancy way of saying this, the invariant ring is exactly the coordinate ring of an algebraic variety, and this algebraic variety is exactly the variety that is given by the algebraic relations that my chosen pi1 to pi m are subject to. Okay, so the interesting thing is also that this map actually has the property that is constant, obviously, on orbits. Okay, obviously, if I only take 2 points that are just mapped to each other by a group element, then the value that I get of pi1 to pi m obviously is the same. So this map obviously is constant on group orbits, but moreover, it actually separates group orbits. That means that also going back, if I have 2 different values in my image, I will come from 2 different orbits, not only from 2 different points. I mean, this I cannot always say, but I can from 2 different orbits. Okay? Very good. So let me just wrap up a little bit because there's a little bit more to look at. Because yesterday we had already looked at the isotypic decomposition of a representation. So yesterday we have only looked for finite dimensional vector spaces. Now I'll abuse a little bit what we did yesterday and suggest we also look at the polynomial ring as an infinite dimensional representation. So this is a vector space, infinite dimensional vector space. We have defined a group action on it. And I mean, theoretically, we only did this for finite vector spaces yesterday, but I mean, this is a very nice infinite dimensional vector space, and the group action actually is very nice. So this hopefully is fine for the moment. So I can just look at the decomposition. So yesterday we defined the isotypic decomposition, which was just, I take my vector space, in this example, my polynomial ring, and I write it as a direct sum over sub vector spaces that share the property that they are made up of the same kind of irreducible representations. So we defined this yesterday very quickly, and we will see tomorrow in the exercises a little bit more concretely in 1 or 2 examples how such an isotypic decomposition looks like. But again, it's just a way of decomposing a vector space into pieces that behave similarly with the group. Okay. And now what we observe, and this is maybe the interesting thing to start with, is my original object of study, namely the invariant ring, can be found in this isotypic decomposition. Namely, it will be just the component that corresponds to the trivial representation. Remember, yesterday we defined this trivial representation. Trivial representation is just when the group is acting trivially, doesn't do anything. And of course, on the invariant polynomial, my group acts trivially. Okay? But there are other parts in this isotypic decomposition, at least if my group is more than 1 element big. And it's very interesting to ask oneself what actually happens to these other components. I just want to briefly mention 2 things. So the first thing is that actually, if you think about this, so if I take a polynomial that is not necessarily invariant, okay, so one of them should be Q and one should be F here. So I see this was already, again, a good example of me making mistakes on purpose, at least for me to wake up. So I take a polynomial, Q, which is in one isotypic component, and I take another polynomial F that is invariant. And what one can check out with the properties that we have established is that when I take Q times F, this will be a new polynomial, and in particular, this polynomial will be living in the same isotypic component. So this was now is maybe now a little bit quick. So if you don't follow with me, bear with me for a moment, and we'll see this tomorrow at a concrete example. But what this actually means is that this isotypic part is is actually also a module over the invariant ring. And in fact, one can show that this is also a finitely generated module. So there are finitely many polynomials, f1 to f whatever, that generate these isotypic components as a module over the invariant ring. So a module is just the same thing as a vector space, but instead of over a field, you look at over a ring. So I have a ring, I look at a base, sort of, and finitely generated. So they generate a generating set, not a base. They generate this space as a finitely generated module. So again, this is an infinite vector space over C, but suddenly when I look at it as a module over the invariant ring, it becomes finitely generated. And again, we have also bounds on the degrees, and in particular also the polynomial ring itself is a finitely generated module over the invariant ring. So let me just give you one example for that, which we will discuss a little bit more tomorrow. So if I just look at now a very simple example, namely the symmetric group S2 acting on the two variables x1, x2 by permuting them, then we actually have that this polynomial ring in x1 and x2 is generated as a module over the invariant ring of the symmetric group by 1 and the polynomial x1 minus x2. So that means that every polynomial that I have, doesn't need to be symmetric, can be written as a symmetric polynomial g0 plus another symmetric polynomial g1 times x1 minus x2. This is what it means to be finitely generated. So every polynomial can be written as that. And in fact, this representation in this setup is actually unique. So then it means that our polynomial ring is not only a module, but it is actually a free module. So I just want to briefly, yes?
In the previous example, what is the character there?
Say it again, sorry, I didn't hear.
What is the character there?
The character is just, so I didn't mention this. So the character here is just the sign of the permutation.
Sorry?
1 or minus 1.
1 or minus 1. Alternate.
1 and minus 1. Okay.
1 and minus 1, yeah. Okay, so let me just to close a little bit. So this actually makes now interesting to what extent these things that we have seen about the symmetric group are actually more generally applicable. And there's a very nice selection of groups that actually share a property, which is so-called reflection groups. So a reflection group, just very briefly, is a group, or actually it's not the group, but it's the representation of the group that is generated by reflection. So a reflection is just what you think about. You have a hyperplane in your space, and the reflection is just taking one element and mapping it to its mirror on the other side. So this is what we call the reflection. And we say that a group is a reflection group if it is as a group generated by its reflections. Okay, so the symmetric group, for example, can be seen when it acts on with its natural action on the n-dimensional space, can be seen as a reflection group, because then we have that these transpositions, they are actually given by reflections. So this is a little bit high level philosophy. One has to be a little bit careful, because again, I say reflection group as if it were a property of the group, but it's very important to always remember it's not necessarily only a property of the group, it's a property of the group and its reflection, its representation. Sorry. Okay, so there are a lot of such reflection groups. Actually, they can be really nicely characterized with combinatorics, But the important thing is there is a very nice theorem by Shepard, Todd, and Chevalier that actually shows the following. So whenever I have a group with a finite dimensional representation, then the following are equivalent. The group is a reflection group. Its invariant ring is a polynomial ring, and the polynomial ring is a free module over the invariant ring. So this very beautiful theorem, which we will not prove, actually tells us that there are some groups that are very well understood, for which invariant theory becomes very beautiful and very easy to understand. In all other cases, apparently, this is not the case, and there is much more work that is necessary. Okay, maybe just to close, I mean, one can also look at another algebra, and this we will maybe do also on Thursday a little bit, so that's why I just want to briefly mention it. So I can look at another algebra for finite reflection groups, or more general, I can just look at the algebra again that is generated when I take the ideal that is generated by my invariance and I mod it out from the polynomial ring. I get an algebra, and this algebra is called the co-invariant algebra. And there's another theorem that we will use on Thursday, so this is why I will just briefly mention it, but we will come back on Thursday. Actually, this covariant algebra has very nice properties, namely it's a finite dimensional vector space in general, but it also has a group action, and as a group action, it's actually isomorphic to the regular representation, and one can actually use this to get a nice basis for this free module of polynomials over the invariant ring. So this was now at the end, again, a lot to digest. So to wrap up, let me just say 4 things. Invariant theory is a very beautiful topic connecting to different aspects of algebra and algebraic geometry, which is very nice to actually dive into and learn a lot about groups, but also learn a lot about algebra. We will use the things that we have seen on Thursday and Friday to actually make concrete use to simplify computations in instances when we have a symmetry of a problem. There are still many open questions in this area. So if you're looking for challenging problems, nothing is better than working on a problem that has already been unanswered for 150 years, right? That's either the sure road to fame or to misery. And what I wanted to also highlight is that all the things that I presented here so far only scratch the surface, and there are many more things to actually learn about invariant theory, but these are the things that we will be needing most on Thursday and Friday. And with that, I just want to come again to a beautiful picture from last night to make you all aware that this place that I'm at is a beautiful one. And I want to quickly steal 1 minute of your time to also advertise for if there are master students amongst you, or if you know talented master students that are looking for a PhD position. We currently have a PhD training network that is looking for PhD students. So there's 15 positions. There is this network, interesting partners. Look at the website if you're interested, or forward it to potential candidates. And with that, I thank you very much for the attention.
Is there any question?
Cordian, thank you very much. Again, a wonderful talk, very exciting one, a roller coaster ride. Just
roller coaster, yes.
Yeah, just go to your slide number 20. Where you explain distortion part. So this is a definition. So it means the reflections are going to give. So if I collectively see the definition and then the theorem, so it means torsion part is coming through the reflection only.
Sorry, this again, I'm very sorry, this was a little bit quick. So I just wanted to mention it because whenever I prepare those slides, I think I have so much time, and then I realize that the time is almost up, and then I wanted to give you a nice lunch break. So I have these for finite reflection groups, we know that there is always a minimal set of generators pi1 to pi n, which are algebraically independent. Those I can use to define an ideal. They define an ideal in the polynomial ring, and I can look at the quotient of my polynomial ring with this ideal. Okay, and then a little bit of algebra tells you already that this will be a finite dimensional C vector space, because I mean those things are algebraically independent. And this is what we call the covariant algebra. And this covariant algebra has very nice properties. Namely, it has the property that as a representation, so I then also can define a group action on this vector space, this algebra, this covariant algebra, and which is just the action that I get after modding out invariant polynomials. And it turns out that this is isomorphic to the regular representation. And I understand that maybe at the moment, this sounds still a little bit technical and not really so exciting as I am excited, or I was excited when I learned about this result for the first time some years ago. But it's a very beautiful result, and it actually has a lot of applications that we will see on Thursday.
Yeah, definitely the theorem, the statement of the theorem is quite intriguing. It is, yeah, the isomorphism.
Exactly.
But how these do you have any example, some quick example where one can see this theorem?
So okay, okay, we can go back. We can go back. Actually, we have seen this theorem already.
Yeah.
Okay. So if we look at this example, we have the symmetric group in two elements. The generators are just the polynomial x1 plus x2 and x1 times x2. So the first and second elementary symmetric polynomial in two variables. And now if I have not really, I mean, so now if you would do this construction, so you take the polynomial ring in two variables and you mod out the ideal generated by x1 plus x2 and x times x2, you will get a two-dimensional vector space, and this two-dimensional vector space will actually have as a basis the one polynomial and the polynomial x1 minus x2. And then this, what we have here, this expression here, virtually then realizes this tensor product. So this
So
is maybe now
X1
also a
minus
little bit abstract and not so clear for the moment, but we will come back to that on Thursday, I promise.
Okay. Thank you very much.
Okay, is there any other question?
There's
Excuse me, Professor, do we have neither bound for infinity reductive groups or not?
Sorry?
Do we have a neither bound
we have
for
bounds. Yes,
infinity
we also, there's also, I
reductive
mean,
groups?
this was, I mean, there's many more and better bounds than Noether's bound. And yes, there are other bounds also for reductive groups.
Oh, okay. Thank you very much.
Other
I mean, one of the reasons why I stuck here with finite groups was just that the definition of this Reynolds operator is much easier for finite groups.
Any
you
question
very
from
much.
IBA, Karachi?
No question.
No question.
Cordian, just out of the bloom from the history. So Gordon and Hilbert has a long conversation on the Hilbert basis theorem proof, and where Hilbert was trying to build this particular analogy to give a proof of Hilbert basis. But I think Gordon didn't accept it initially because the argument was not. Yeah,
I think so. I mean, I'm not an expert when it comes to history, so I now I have to be very careful because I'm also recorded. But yes, I think this was really, I mean, this was really a little bit. I mean, they didn't accept it as a proof because, I mean, so the proof that I gave, I mean, as you said, it relies on the basis theorem essentially, and I mean, this is a very spooky theorem. I mean, if you are a person in the 19th century and you're used to actually calculating things and being happy to have something in your hands, a theorem that just says, well, there exists somewhere, good luck finding it, I think is the worst thing that you can imagine. And this is why, I mean, I thought, as far as I understood, people around Paul Gordon they rejected this idea that this is not a theorem, because what actually good do you have from it? It's just saying, well, there are some, but doesn't really give you any ways of actually doing it, getting it.
Mhm, mhm.
And if you, I mean, I think you have done this last week a little bit with Gröbner bases. I mean, in general, it's really hard to find generators of an ideal, right? I mean,
There is one place where you use the Grosvenor basis stuff for the algebra. So you mean you are going to address the Grosvenor basis theory, which for the ideal which is coming, which is generating that
exactly,
algebra?
exactly
Okay,
for the
okay.
ideal. Yeah, yeah. And then we use this trick here.
Okay, thank you.
There is no other question, so let's thank the speaker again. Okay, thank you so much. Could you please share your slides of lecture 1 and 2 with us?
Yes, I will share my slides, also the ones from yesterday. And I
Yes.
hope you all have a nice lunch break now.
Okay, there is another question that could you please refer a book, standard book?
Oh.
Yes, he has referred. Yeah, yesterday. Yeah.
I
Any
I
recommended book?
can give more references to books also. I can
Okay,
give more
okay.
references to books if
Okay,
wanted.
okay, okay.
And
Thank
in
you.
particular, let me also say, if somebody of you has so tomorrow we do a tutorial where I try to do some concrete things. But if somebody has a concrete question that he or she wants to have answered tomorrow, you're also absolutely fine to send me an email.
Okay, okay. Thank you so much. Thank you so much.
Bye-bye.
Bye, bye. See you tomorrow.